Okay, so now we're going to continue with this slightly technical part of the lectures. So just before the break, what I introduced were these two concepts. One is the window function. Window function basically focuses in on some part of space, and it allows you to calculate what's the overdensity in that part of space. And we also saw that there was a likelihood distribution, there was a probability of a given overdensity, which we are taking to be one of these Gaussian functions of this form. So we can take that as a mathematical thing more than anything else. And crucially, this thing has a sigma, a scatter in this distribution, and that's related to the power spectrum. And then I went through very quickly that you can empirically go around and calculate the variation in mass in boxes of size r. So now you can also see that if I now do the same exercise again, there's another point I want to also highlight. So now if I make a very small box, let me just make a small box here. The variation that I get here between the different measurements, sometimes is 0, sometimes is 1, is large. Okay? It goes from 0 to 1, sort of the full range. Now imagine I make a big box. Make one here, make one here, make one here. And or I can make a really big one. Okay? The variation when I have a single box is 0. Okay? No variation, because regardless, as long as the box is so big it encompasses everything, regardless of where I place that box, I'm going to get the same number. There's no variation. When I make a very rather big box as well, the variation will typically be smaller. So this variation that I calculate will depend on the size of the box, or the size of the window function. And that's what I'm calculating here. And so this sigma value, it really measures how, if I make a box size r, how does the count of galaxies vary from position to position on the sky. We do that empirically. From a theoretical point of view, I can use this expression to calculate what the predictions are for a given model. So what I wanted to do now was to do that calculation. And what we're going to start with, and I have it all written down here, but I'm going to do it step by step anyway, because I think this is quite an important calculation. So first, you have to remember or be reminded that this is basically related to the normal power spectrum in this way. And that was a slide somewhat earlier here. There was a summary here where it said that this squared is, I forgot the 1 over 2 pi square. It's always a pain to remember. So that's another way of writing the power spectrum. It's exactly the same content. Sometimes people like to use that, sometimes they use that. Okay, so let me go back to this integral again. Okay, so now let's look at this expression. Let me write it down. So I want to calculate this sigma of r. It's an integral over 1 over 2 pi squared k cubed times a window function. And I'm going to make a window function that basically just goes from 0 to kf. Some simple cutoff in k space, and then p of k. and then dk. So now we can actually put in some power law power spectrum. Before the break we saw that's often the case. It might change depending on k, but for some region of k space, the power spectrum can be written as k to some power. If I put that into this integral, I get an integral which is k n plus 3 minus 1 dk, and that's going to be proportional to k to the n plus 3. Okay? That's essentially this relationship here. Now in this particular case, I wrote down, I used r, so I said sigma r is proportional to k to n plus 3. But k is Fourier space is not somewhere we like to be. So this is much more useful to recall that k is proportional to 1 over r. So I'm ignoring all the proportionality constants in here, and I get that this goes as n plus 3. So you can see if n is on positive, say n is 0, this basically goes as r to the minus 3, and it says that the variation, so the variation as you put down these boxes, goes down to larger scales. It just means that the universe becomes smoother and smoother on larger scales. And there's a lot of structure on small scales. If n approaches minus 3, then this becomes scale independent, and that means that the variation in the field, it's an equal amount of structure on small and large scales. Okay? That's what this really will tell you in that case. So this is related, closely related to the power spectrum, of course. It's the same story as I gave with the power spectrum before the break. And it's also useful to take this into the range of masses, and it also means that if I wrote it in terms of mass, it is proportional to r to the minus n plus 3 over 3. Okay. So this quantity, this sigma, it really defines something about how likely it is to have a big perturbation on a given scale. So what this says is that when this, say when n is 0 here, it tells you that it's not likely to have a big structure, big overdensity on large scales. It is very likely to have big overdensities on small scales, because that's when sigma becomes large. So it basically quantifies how likely is delta to be far away from 0. 0 means no overdensity, and that's the average. And this tells you how likely it is to be far away from 0. And it says, okay, it's dropping with scale. So on large scales, it's not likely to be far away from 0. So there's some other scaling relations. I'm not going to write them all down, but you can remember that in the during matter domination, the overdensities evolve proportionally to A. We did that before the break several times. And A in the matter-dominated era, that's what we did in the morning, is proportional to time to 2/3. The correlation function, or the power spectrum, those are equivalent, they both depend on the density squared. And they then depend on A squared, or equivalently, time to the 4/3. And the sigma finally, sigma depends on the overdensity, so it's proportional to A or proportional to T to the 2/3. Right. Okay. So this is what we derived before the break. It's how the power spectrum changes. Remember, this is the change of slope from k to the nth power to k to the n minus 4 power for things that enter the universe into the horizon during the period of radiation domination. Okay, so that's the change of the scale of P of k. This is equivalent, very closely related to the sigma, which we derived over here. So I can use this expression here. Oh, sorry, there's a big bad typo here. That should say m, of course. So I can do the same evolution, just using that sigma squared is proportional to the power spectrum times k to the third power, to say how this variation in the overdensity depends on the mass of the structure you're looking at. Okay. Now, this is all I'm doing is linear theory. Linear theory has no galaxies, because linear theory means that the overdensity is less than 1. So it means that the density is less than 10 to the minus 30 or 10 to the minus 29. No galaxy is that diffuse. So you need to know when things go nonlinear. That's when things happen. So nonlinear happens when delta, the overdensity, is about 1. And that happens, there's a chance of that happening when the sigma, which determines the width of your Gaussian distribution, approaches 1. Okay, when this is 1, then you have, one chance in 3 to have a perturbation that's greater than 1. So then you can try to estimate when this happens using the relationships that I just showed you earlier. These ones here. So this tells you how this depends on A and depends on T to the 2/3. So you can set this equal to 1, call that the nonlinear time, and that depends on the initial time that you start your perturbation and the time of nonlinearity to 2/3. And that gives you an estimate of the time of nonlinearity, and you know this relationship for sigma of m, which is this one I had written down here with a typo. You can plug that in, and it tells you, and now this becomes more interesting, it tells you when the time of when an object of a given mass goes nonlinear. And so this I'm going to copy over here. I'm not going to do the full calculation. They are essentially trivial. But this result is not so trivial. So it says at the time that an object or an overdensity becomes 1, so an object becomes nonlinear, is proportional to the mass, now I have to get the right order here, to n plus 3 divided by 4. And so what this tells you now? Well, first thing to keep in mind is that in most models for the universe, n is going to be greater than minus 3. Okay? So n is greater than minus 3. What that means is that this exponent is positive, and it means that objects that are more massive go nonlinear later. Okay? That's essentially what we call a hierarchical universe. A hierarchical universe is one where small structures go nonlinear first and then bigger structures later. And that's what this is telling you, that if n is greater than minus 3, this is positive, and more massive structures go nonlinear later. Okay, this is m to some positive power. If n is equal to minus 3, then structures of all scales go nonlinear at the same time. You form things at the same time at all kinds of masses. Yeah?
So measure n can give us information about if the graphical model is good or not.
Yes, exactly. And so that's indeed what people did a lot of times in the beginning. And so there's the danger of boring you and boring myself. Let me just go back to that relevant slide, because so this is what the observations look like, and this effective n is the slope. We now can measure this, and you see it curves a bit, but it goes between -2-ish to -2.5, something like that. And so we know in this regime it's currently hierarchical. And that's about as far as I'm going to take that. It turns out to be a bit more complicated, because then other things come into play, like gas and stuff like that. So to be more precise than that is hard.
So again, the value of n is close to
-2-ish, yeah. Something like, yeah, -2.35 is probably the best guess for things like the Milky Way. Something like that.
Okay.
So it's not 3. No, exactly. -3 would be weird. Would be quite an exciting world. But it means that, you know, if you put it in, and if you just write it out, it means that this goes as m to, so that's, say it's 0.5, so it's 0.5 to 4. So 1/8, all right?
Yes.
So
1.25.
Exactly. But it's a slow power. It's a low power. So there's not a big difference between low mass and high mass structures. It's still hierarchical, but it's not a dramatic difference. Don't over-interpret this thing, okay? This is useful for hand-waving arguments. It's not useful for quantitative statements. Okay? But it gives you more or less the right idea. Okay, now my pointer doesn't work anymore. Okay. But I should also emphasize this last sentence here. Okay? My arguments here are on dark matter. I'm not arguing about galaxies. They might form in a different way. So this argument is gravitational only, is only gravity, nothing to do with gas, dissipative gas. Right, so now I'm going to come to the clever cheat of spherical collapse. So the idea here is that you take the universe as it is, completely uniform, and then you put a tiny little overdensity that's spherical, very, very slight overdensity inside that universe. And you assume simply that the background is flat, and this is slightly overdense. Now the nice thing about this is that from Birkhoff's theorem, which is the equivalent of the Newtonian theorem about shells, this thing, spherical thing, doesn't care about the surrounding universe. It only cares about itself. It's ignorant of the surroundings. So this will evolve as a separate universe from the surroundings, as long as this doesn't dominate the mass. Okay? So this, we have the solutions for both of those. This is like, it will be a closed universe. We can solve those equations. And we're going to use that as our model for the formation of a clump or a black dark matter halo or a galaxy. Okay? It's a slightly overdense region. It's spherical. It's going to evolve on its own. And the great thing about it is that since it's spherical and completely symmetric, we can solve the equations exactly for this. Okay? We can calculate the evolution of this spherical structure in an expanding universe precisely. And that's very nice, because then we can go into the nonlinear regime of what's happening. It's a bit fiddly, so I haven't given this as a problem set to do, because it will take you a long time to do correctly, probably. But it is fully straightforward to do it. I'm just going to show you the results. Okay. So here is the result for this. This is a scale factor, which is basically some random time coordinate. But it's a scale factor of the universe in this case, but don't care so much. So this is the actual density. okay, then the universe expands, so the density goes down. And in linear theory, the density, not the overdensity, okay? The overdensity is this density minus the background divided by the background. But this is the actual density. In linear theory, the actual density goes down and goes down and goes down, right? The overdensity goes up because the background goes down even more than the object. But still, this is not very exciting if you want to form an object because it becomes less and less dense. In contrast, the true spherical solution is this blue line. So this also in the beginning, it's just a slight overdensity, right? So it follows the surrounding universe in the beginning very close. So it expands with the universe. But at some point, it has enough self-gravity to counter the expansion of the universe. And you come to this region here, where first it reaches a time when it becomes non-linear. So the overdensity is 1. You see there's no sign in the density, of course. The density doesn't care. Overdensity is 1. Then it moves to this region. Here, it stops. Okay? It has gone, it's pulled, the universe has pulled it along, but no longer. It's not going to go any further. And it turns around, and it starts to collapse down fully. And so the density now goes up rapidly, 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 and eventually it reaches infinite value.
Yeah, but this only happens on this sphere.
In that sphere only, yeah.
Okay.
So it's completely isolated from the rest of the universe. So there's no other spheres around, which would immediately ruin this because of tidal effects. But so it's an isolated sphere, it's the only one in the universe, etc. So it's a very idealized situation, but you can solve it exactly. And you can also just use the virial theorem, and that's an easy little exercise to write down. The virial theorem will tell you that this infinite density here happens at 2 times the time. So if this is TTA, some time of turnaround, collapse will happen at twice that time. That follows straight from virial theorem. And the radius in that case, if you don't let it be a point particle, it should be half the radius it was at turnaround. And so we call this, we typically refer to this time, where the equations predict infinite density. We call that time of virialization. So we say that's when the structure actually forms, the real formation of an object. And an object that can reach this, we say will typically be virialized, even if you go out and you calculate the general kinetic energy and potential energy, it will basically be satisfying the virial theorem. Okay, so what's the point of this? Okay, that's an extremely idealized system. You don't really know how to make use of this solution on its own. Why is this useful? Well, it's really useful for one very nice reason. And that is you can take this, and you can compare what does linear theory predict when this happens? What does linear theory predict when this happens? What does linear theory predict when this happens? So if you can make a mapping between these two, you can then use linear theory, which is easy, to predict something about nonlinear things. So in particular, you can calculate what the density is at turnaround, this time when this sphere stops expanding. And that's the relationship between the background density and the actual density. So the density is 9 pi squares over 16 times the background density, so 5.5. The reason why there are all these pi's in here is because the solution to this collapse equation is typically in terms of sinusoidals and cosine functions. At the same time, so now you can match in time, in cosmological time, you do your solution of your nonlinear equation and your linear equation, and you take the same time, and you say, what's the overdensity? Oh, it's 1.067. So what you're going to say now is that, oh, I'm going to use linear theory, and I'm going to say, oh, I'm just going to follow linear theory until I get to a value of 1.067, and then my objects have turned around. Okay? by this correspondence. So I ignore nonlinearity. I just use linear theory, but I use this fact to sort of say, okay, I tick off here. And it's kind of nuts, because linear theory assumes, as we went through yesterday, the delta is much less than 1, right? But I'm just going to ignore that very happily. I'm just going to say, okay, it doesn't matter. I'm just going to pretend that I didn't know that. And yeah, exactly. Nobody, I'm not going to tell anybody. And you can do the same thing with the collapse. And what you find then is that the density at collapse in a flat universe is 18 pi squared, which is one number that people often keep remembering, times the background density, or that there's an overdensity of about 180. Okay? That's when the object virializes. And that corresponds to a linear overdensity of 1.69. And the two really cool things about this. One is that this is almost independent of cosmology. It depends very, very slightly on cosmology, but very, very little. So I don't need to know about the cosmology in detail. I can still use this. I can use my linear theory, take my linear theory until I get delta of 1.69, and I identify all the perturbations that are bigger than 1.69 as collapsed objects. The other thing that's nice is that we can go and we can do simulations, proper simulations, and we will find that if you take a region where the mean density inside that region is about 200 times the background density, that region will actually identify a region of space that's virialized or that is formed. So this actually is a sensible way of defining it, and this is a very useful correspondence. So we use it often in observations too. You often want to know what's the virialized region of a galaxy cluster. And so what you do is you go out, you observe a cluster of galaxies, and you count galaxies inside there, or you measure their mass, and you integrate outwards until the mean density of galaxies, or mean mass of galaxies, is 200 times the background. And you know, okay, that's the radius of my galaxy cluster. It's not always a very good idea to do that, but people do it anyway. Now, let me see, go back to this one. Yeah?
So the linear theory does not predict the stratification, the peak stratification?
No, they don't. No. It really doesn't, because it's really, exactly. So it does this. So density, the real density goes to 0. So you cannot possibly form any object because it is 0 density. So linear theory simply cannot ever do that. And so it's not useful at that level. You need it because at some point you need the exponential growth of gravitational collapse, or something close to that. And what linear theory is, it basically is the first term in a Taylor expansion of an exponential. And that first term in the Taylor, or second term in the Taylor expansion, is never going to catch up with your exponential function. And that's the main, part of the reason why this is never going to work. It doesn't have those higher order terms in it.
Now, another question. But when you have this sphere virialized, it reached this critical density of something. This is something parallel, for example, with a radial collapse and reach Jean's mass. Is it not the same?
It's very similar. It's very similar. Yeah. The collapse equations are slightly different because of the expanding universe in the background. But in terms of the physics, towards the end of the evolution, it's identical to Jean's collapse. So that's exactly what you would. Well, the equations look a bit different, but that's what you get. Yeah, it's so you don't in this particular solution you don't have you have collapse only. You don't have pressure forces. So it's like you can calculate in that way, but so you won't get quite the same solution as you would if you do a gravitational collapse of 1 over square root GT but it's not so far away. Okay, so this is then really what you want to do. You want to use this as a trick to use linear theory. And that's where we're going to get our hands on mass functions. And these equations are quite important for defining that. So this is really, you know, in a way a take-home message that you really should keep in mind. And this is operational. This has nothing to do with theory or anything like that. It's just if I go out in the universe and I see a region in space and I add up all the mass in that space and I get a mean density in that region that is higher than some cutoff, say 200 times the background, then I have a very good reason to believe that that region will satisfy the virial theorem, will have virialized, or at least be very close to doing so. Okay? So that's a physically useful thing to do. It has nothing to do with, that's independent of galaxy formation. It's just a way to say, okay, that's a real object. And so this is often why we use this, is that the objects are not very well defined in the universe. They don't have a sharp edge. They go on, go on, go on. So the only way you can really go about it is that you say, okay, this region satisfies the virial theorem, it's virialized, so I'm going to say that's what defines a real object. And that's what I'm going to use. So that's why we often use this kind of approach. And as I wrote here, this argument would be completely useless if this parameter delta varied wildly. If it was something that was specific for every single clump, this would be completely useless, right? Here it's 50, here it's 200, here it's 70, here it's 5. It would be useless. But because of the argument, basically on this sort of spherical structure formation, we expect this to be quite close to being universal. This is not a fantastic solution, but if you have no other way of getting it, this is a pretty good way of getting an estimate of the right region. Okay, so I thought I'd have a quick quiz back. So normally I have I do this with a small set of pieces of papers. I hope you all have something to write with, because I have some pieces of paper here somewhere. Not my passport. Oh no, I have left them somewhere. Ah, what happened? Okay. Well, that wasn't so useful. So, okay. I'm going to divide this one up in many small pieces then. So now we're going to see how much, and I don't want names on this. I want anonymity. So, well, how many? 1, 2, 3, 4, 5, 6. Okay, they're going to be really small, these ones. So, okay, let's see. There, I got 8 here now. Okay, so it should have been a bit bigger, but you know, this is big enough. So I only want a yes or no, A, B or C, and you can ignore 3 because there is not enough space to write. And then we see how things look. Here you go. Oops. So there you go. You get one too. Okay. All right, I'm going to gather in some again. Just the two questions. Uh-huh. Well, I'll get them. So actually, when you're finished doing them, you can come up with them here to me. I'll check them all together. So. And I'm going to turn it off. I've got enough time. And let's see if I can bring up the solution for you as well. It might be a useful one too. Okay, just trying to see if I had it here. Yeah, okay, so I find it. So I'm not going to put it up until I've gotten the solutions from everybody. So, let's see. Okay, thanks. Yeah, all right, thanks. That's everybody's? Okay. Oh, okay, yeah. Right. Okay. So, let's now see which one. Okay, so I get everybody.
Do you need some help?
No, I'll do that. This is easy. I need to write at about the same time, and you might actually know the handwriting. So, oh, sorry. Probably useful to have. Now bring it up again. Okay. Oops, it's one too many. More here. Okay. So it's already different from what I'm used to. Oh, and C got one too. Okay, so usually what I get is that I get almost the same number here as there, and I get pretty much equal spread here.
Okay.
It's the most common way. This time I didn't do that, but unfortunately I got most of the answers on the wrong one. So I'm not going to they're not going to ask you why you answered the no, but does anybody that answered yes want to say why they answered yes?
Well, it's a power spectrum, so it's not like the usual way we understand functions. That's why I asked the same.
Uh-huh. Okay, that's not right. But it's worth a try. Anybody else that answered yes that would argue for why it's yes? So where in this plot is the primordial power spectrum?
Yes.
Exactly.
Value at
It's,
the beginning.
it's on this side, exactly. And as things change, they change the slope. Okay? So the primordial power spectrum is here. And you can compare against this line, which is the same line in all the different panels, and you can see that the slope is the same in all different panels. Yeah. So they have the same slope. Now you could argue that that there's a difference in normalization, okay? But it says here arbitrary scaling because it becomes a bit random how the normalization is set here. I set them to have the same peak essentially here for plotting purposes. They're not, you can't easily do it like this. So the primordial power spectrum here is the same. So they all have the same primordial power spectrum. And you can always look for that at this end. And just ignore the fact if things go up and down, because that has very little meaning in itself. And now you might, so instead of doing the calculation, let me bring up the solutions. So, well, maybe I should just drag it over here. Okay. So this is how I would expect the solution to be. And so the horizon, right? The horizon was where the power spectrum, the power spectrum changed slope corresponding to the horizon at matter radiation equality. And that depends on radiation and matter density. Now you could tell me, and you would be right, that the question as I gave you was not solvable. Because you could change the temperature in the current day universe, and you could change the position of this peak arbitrarily. But if you say that the temperature of the cosmic microwave background today was the same in all the different cosmologies I was plotting, then I can infer what the matter density is from this expression. And you can calculate the horizon size, and you can estimate which ones are the strongest, the highest density.
So that is where the change of slope is irrelevant.
Exactly. So in this particular case, let me go back. The right answer, and I think there was at least one right answer, is at least one got it right. I don't remember if there were more. Is A and D, and that's very sharp-eyed if you could spot that. I never deduct any points if anybody doesn't get that, because it's very hard to read off the true peak here. You have to say that the peak here is the same as the peak here, and it doesn't even look like that, right? So it's very well thought.
The dotted line is the same as A.
As the first one, yeah, exactly. So this position, when it is moving that way, you have higher density. Moving that way, you get lower density. That's just the size of the horizon at the matter radiation equality. The three, some of you tried to explain that. I didn't write them up there because there was not enough space to write something meaningful. It was hard for me to understand what the argument was. Now the main difference between these ones is that this and this is the same, except there's less matter in the universe here. This and this is the same, except I put in neutrinos. And the neutrinos, they do this free streaming, which I skipped out a little bit. I said it wasn't so important. It is a bit important because it turns this to be even steeper, to be steeper than -3. And finally, this one is the same as this one, but I put a lot of neutrinos in. So all of these differences here is due to neutrinos. That's what's cutting things off here. Any particle that's free streaming will do this. It will wash away structure. That's that lambda Fs that I talked about.
Why in the case B and C, the dotted line is behind?
Yeah, so here it is because the matter density is, so in this case there's quite a lot of neutrinos. So the total density is lower than it is in the dotted line. So that's why it's moving that way. But there's a lot of neutrinos, that's why it's moved a little bit to the right relative to B. In this case, I normalized it so it had exactly the same matter density. And the only difference here is that neutrinos just basically streamed out of the overdensities here and washed them out. So that's what's going on. Okay, so now you've seen how you can take a power spectrum and read off the cosmological parameters. You can actually now go in and measure here. What's the size this is in moving h over megaparsec, and you can use that then to calculate what's, with the current day temperature, you can then calculate what's the density that I put into my model. And I bet you will get the wrong answer, but anyway, that's... I could never get it right. So I think there's some subtlety in the position. I get it within a factor of 2, but it's hard to get the peak right, and then there's probably some second order effects in the position that I didn't take into account. Okay, so I would say, well done. Okay, this is not usually when I do this test, people don't get this right. And here you clearly got A and D clearly won out over B and C. So I would say that's very good. I'm positively surprised. It's not normal that I get that result. But I normally get a better result on this one. So, so I guess it balances out. But well done. I was surprised that they got so many A's and D's here. That's good.
No, but the first one was maybe the curves.
It might be the normalization.
Starting at the same highest.
Yeah, it might be that, but confusing. So I will assume this was an accident of plotting, and that this reflects your understanding. All right. Now we're going to get down to something called virial relations. So now I have this way of calculating what's a structure. A virial structure is a spherical collapse system. So what I then do is I say that it's virialized when the density inside is greater than some constant times the mean background density. And typically, I will take this to be the critical density. People use slightly different norms. But then you can put this in. So we can do that very easily, of course, because the density is just the mass over its volume. Okay? And we say that radius is the radius of virialization. Okay? So that's the density, and this should be, let's set it equal to delta C times the critical density. I have a greater than in this particular case, but this now allows you to solve this. These are parameters that depend on cosmology. This is the object's mass, And this will tell you what the size of the object is. So now we suddenly can connect cosmology, which is on this side, to the properties of the objects we're forming. So we're now getting closer and closer to forming galaxies and other structures. Okay? And that's the solution. When you calculate that, you don't want to remember that equation, but you need to remember how to derive it. That's basically the idea behind this. And of course, it's easy. If you remember this, then you can fill it in. If you forget this one, well, then you don't have a chance, but that's your problem. You shouldn't forget it, or when I give an exam, I actually keep it on a cheat sheet, which I actually included for you as well. And so this radius of virialization depends on cosmology, gravity, the mass of the object to 1/3, which sort of makes sense for a radius, and the redshift, and the matter density. And I approximated here the Hubble constant, ignoring cosmological constant. Okay? So this is okay at redshift, say, between redshift 20 and redshift of 1. This is a very good approximation. But it might not be good today. But so notice one cool thing about this. So if you have the same object, if I form a galaxy that's 10 to the 12 solar masses, it's the same galaxy formed at redshift 2 is going to be 1/3 of the size of the galaxy if it formed today, right? Because of this 1 plus z. So it means that galaxies, immediately you can see here, that galaxies that formed early in the universe were smaller at the same mass than galaxies forming later. Immediately a prediction that you can go out and you can compare against observations. And I had a problem like this for your hand in, but then I realized it probably was a bit too long to actually calculate that, but it works remarkably well. Not really well, but quite well. It needs some improvements here and there to get it really right, but it works quite well for the real universe. Okay, so this immediately tells you something interesting about galaxies and why galaxies at high redshift that are forming at high redshift are smaller. So you would expect things that are more compact to form earlier than things that form later. You can put in some scaling relations. It's often very useful to put in some typical numbers to read off what it means. So the virial radius, if you put in values for the Milky Way, which is a halo, dark matter halo of, say, 10 to the 12-ish solar masses, typical density of the universe, you get that the radius, the virial radius, is a few hundred, say, 500 kiloparsec, or 380 h to the minus 1 kiloparsec. So that's typical virial radius of the Milky Way. That's much bigger than the galaxy, okay? But this is the size of the dark matter halo that our galaxy lives in. It probably isn't as big as that, but it's not sort of on that order of magnitude. So basically, we're out, you know, the galaxy is probably 30 kiloparsec in size. And this is telling us that the virial radius, the size of the dark matter halo of the Milky Way, is probably 10 times as big, or at least, you know, that kind of order of magnitude. And it gives you an idea what the size differences are. At high redshift, the typical galaxy that you form at redshift 9, 10 is of the order of 10 to the 8 solar masses in dark matter halo size. And the size then is both because it's small and because it's at high redshift, it becomes very compact, 1.6 kiloparsec. That's really, really small. 1.6 kiloparsec at redshift 10 is about 0.1 arc second in the sky.
It's the bulge of the host.
So it could also be the bulge of a galaxy, indeed. So that it might be, but that's a different story.
Yeah.
If it is a separate galaxy, the size is really small. But yeah, in some situations, this could be the bulge of a galaxy. If it's an isolated galaxy, it's a very small one. But it tells you that these things are going to be really hard to resolve because this is the halo size, right? The galaxy is smaller than that, right? In the Milky Way's case, it's a factor of 10. For these ones, probably less than that, but you know, they're small inside there. So this is very useful as an idea, guideline for what kind of size you're talking about. If you're seeing a galaxy, a satellite of the Milky Way, and you want to ask, is this in an orbit around the Milky Way? Is it bound to the Milky Way? Well, if it's well outside of this radius, then probably not. Right? It's outside the dark matter halo of the Milky Way. It's probably not bound to the Milky Way. If it's inside, then maybe. We can also, just simply taking the virial theorem, and the full virial theorem you never use, because we're lazy. But basically the simplified virial theorem, which says that twice the kinetic energy is equal to minus the potential energy of the system. You can put that in. The potential energy of a spherical distribution for a uniform sphere, it's 3/5 g mm m squared over the radius. But more importantly, you can also write down what the kinetic energy of the structure is. It's in this form. It's just writing down the kinetic energy per particle. And it gives you a virial temperature which depends on the mass and some physical constants, the radius, and the reduced mass. So if you have a fully ionized gas of hydrogen and helium, this one is 0.59. So it depends on how ionized it is. It's the mean mass per particle. Okay, so if you have only hydrogen and it's neutral, then the mean mass per particle is 1 hydrogen mass. If you ionize the hydrogen and you ignore the weight of the electron, then the mean mass would be half, right? Because you have twice 2 particles, but you have the same mass. They have the mass of hydrogen, so the mean mass per particle is half of the hydrogen mass. If you have ionized hydrogen and helium, then this is 0.59. So this now gives me an estimate of what the virial temperature is. And that virial temperature is important because it is the temperature that gas inside the dark matter halo typically will reach. And it's much more useful to do it in this form. Okay. So on this side you have Milky Way halos today. So tomorrow we will look at cooling and the cooling effects of gas in halos, and that's crucial for forming galaxies. But for the moment we can sort of ignore the aspect. Basically it says that the Milky Way halo, gas in the Milky Way halo would be around 150,000 Kelvin. And that means that if you want to look at it, it's really hard because it's completely ionized, and 150,000 Kelvin isn't enough to emit hard X-rays. This is hard UV, soft, very soft X-rays. It's extremely difficult to detect gas like this. So it's a possible reservoir of baryons that we just can't see. If you go at high redshift, redshift 10, the same scaling relations, the typical temperature is about 4,000 Kelvin. And now if you remember back yesterday when I talked about the reionization of the universe, I said that you needed temperatures of the order of a few thousand, say 5,000 Kelvin, 6,000 Kelvin, in order to ionize hydrogen. So that means that in halos of this type, you're about right in terms of velocity for collisions between particles to have enough energy to ionize hydrogen. Okay? If the virial temperature was lower, then basically these particles will just move very slightly and touch each other, but they won't be energetic enough to ionize hydrogen. So these start becoming interesting because even if you don't have a source of UV photons, even if you don't have stars, you could start creating free electrons by collisions. And those free electrons, and that we will talk about a lot tomorrow, will help cool down the gas a lot and will help accelerate the formation of structure and creation of stars, etc. So this is quite important as well. So I showed this one yesterday, or part of this one, showing the difference between what happens in halos of different sizes, but now you understand a lot more of what's going on here. So first, what we're plotting here on this side is overdensity. It's density divided by the mean density. This is temperature, in log temperature, from 10,000 Kelvin to 10 million Kelvin in yellow. This is the amount of gas over the mean baryon density, it's the density of gas. And this is temperature again. It's the same, these panels are the same as these panels, but these are more zoomed in. Okay, this is the central region, this is the bigger region. Okay? So overdensity temperature, overdensity temperature. And this white line here is now the virial radius that we can calculate from the equations I just showed you in previous slides. You take this mass, and if I told you in redshift 2, you plug that into the equations we just had, you get a radius. And that radius is what's plotted as this white line here. The temperature inside here, you can also estimate the virial temperature from the equations on the previous slide, and you can compare them to the temperature inside here. And you see, at least you see that the temperature goes up as you move this way. And it will go up roughly in the same way as we did here, mass to 2/3 power. More or less, it goes like that. So, whoops. So this then gives us a picture of all the ingredients in this diagram. Of course, we are making idealized structures. Real structures are not radially symmetric, azimutally symmetric. They are actually more complicated. But we get the mean trends right, even though details differ. So now we're going to go from that and now move to the mass functions. But so if anybody have any questions about these virial rate relations, it's a good time to ask them. Because this is one of those things that might seem quite straightforward until you have to derive them yourself and you get every constant wrong.
I have a question about the last slide.
This one.
No. This one.
Oh, oops, this one. Yeah.
Yeah. Here, if we use, for example, hydrogen, it's really easy to put the mass of particles.
Yeah.
Then, what do you do if the particles are dark matter, for example?
So you don't normally, so this is, so I have written M gas here in order to emphasize that this is baryons, because
It's only for baryons.
because as long as the dark matter particles do not collide with anything. If they don't collide with anything, they can't gain velocity.
Okay.
So if they could collide with baryons and gain velocities from them, then you could have a temperature in here. And there are some types of dark matter where that might be meaningful, but in general not. So that's why I forgot to say it actually, but it really means this because the temperature really only makes sense for baryonic matter.
Okay.
So indeed,
There is no theory or collapse for dark matter.
so dark matter can virialize because that's a gravitational process, but they can't cool any further.
You can't calculate any energy.
Not an energy per particle because they can't gain that energy itself. You can calculate a virial temperature, but it won't have anything to do with the microscopic temperature. Here I'm making the argument that you can identify this temperature with the microscopic particle temperature. That's why I have a 3/2 MKT. But it is indeed true. So for the dark matter, I can tell you its virial temperature, but it won't have anything to say about what the individual particles of dark matter is doing. When I'm doing it for the baryons, I actually argue that it's likely that they will have this temperature. It's not obvious that they will, though. That's actually not a trivial result, and I'm not going to spend time on it, but it's not trivial that it is like that. So there is quite a lot of subtleties about this, yeah. Okay. Right. Okay, so now we can try to pull some of these things together to calculate mass functions. And we're going to start with dark matter halos. Because I don't want to touch on galaxies, dark matter halos is what we want to start with. And there are three ingredients in here. The first one is to use these spherical collapse models. And that's to define what you mean by an object. I need to have some criteria to say that something is a dark matter halo. I have to have something. I could be any random thing, but most definitions I would come up with would be meaningless. So I'm going to define dark matter halos in a useful way. I hope. So I'm going to write the dark matter halos, DM halos, are overdensities that are virialized, that are virialized and I'm going to define the time they form by this equation here. They form when the linear overdensity is greater than 1.69 times 1 plus z. The 1 plus z is just to take into account the growth of structure that's proportional to A. Right? This is 1 over A. So that's the definition. So I'm defining, this is a way I use to create, to say what's a formed object. And then I have that. And then next thing I have to do is I have to say what's the chance of having this value? What's the likelihood of having that value? And the likelihood of having this value is given by this Gaussian distribution, which I told you just to accept. Okay, we're not going to derive it in any rigorous way. And that means that my object basically is defined when I have this like inequality satisfied. And this is exactly what I wrote down last time, before the break at some point. The P of delta greater than some delta cutoff, that's what I wrote down before the break, is an integral from the delta cutoff to infinity of 1 over square root 2 pi sigma of r, or I could use sigma of m, they're going to be equivalent, e minus delta squared 2 sigma squared of r d delta. Okay. So that's just an integral that's telling me what the likelihood is of having delta greater than delta c. It's just what this probability means. So if you know probability theory, that makes sense. If you don't know probability theory, you can just take my word for it that this is how the likelihood should be calculated. And then we come to something which is known as the Presch-Schechter ansatz from some years ago. And they are saying, basically what's written here, that the fraction of mass elements in halos with mass greater than m is equal to the probability of having delta smoothed on some scale r, which is what I had over there, P delta greater than delta C, where delta S is the density field smoothed on the scale m or r. Okay? So it's exactly the equation I wrote down there. And you can do the integral. What it is it's a complementary error function. And that's the likelihood distribution. That's their ansatz. That's their proposal. And then you can just use that. You say, okay, that's where I'm going to start. And it will tell you that the fraction then should be, and this is their bit that they didn't put in their ansatz. So you see, there's no question of factor of 2 here. But then they found out that actually to get this to work, they had to multiply it by 2. And there is a reason why they had to multiply it by 2, but it took over 20 years before people understood why. And the reason is what they are calculating. If you think of an overdensity as a function of, it's a function of time, or no, it's a function of scale. So I smooth the structure on different scales. It's a big scale, small scales. As I smooth it on different scales, I might at some scale be above the threshold, but then on smaller scales I might be below the threshold. And it's accounting for this structure. So you have structure inside structures. You might have something that's overdense on a very large scale, but actually the inside is underdense. And that you have to account for that right. So I'm not going to go into details on that. In the lecture notes that I have on the web, if you want to know about it, there is a section dedicated to this called the extended Pressure theory. It's something I long since stopped teaching because it's confusing and rarely useful, but sometimes it's very useful. And so it's a bit of an annoying little thing. So it's in the lecture notes. I'm not going to talk more about it. Just accept that this factor 2 had to be there. And for 20 years, there was no justifiable reason for putting it there. But eventually, people have put this on proper mathematical footing, and we now know it should be a factor of 2. So it's correct, even though it was never put in on the basis of anything. Okay, so now how do we get a mass function from this? Well, you get it like that, but that probably doesn't mean anything. So what I want, I want the number of dark matter halos in a small mass range at a given time. For doing that, the first thing I want to do is I want to calculate what's the mean number of halos that I can have. Okay? So if I took all the density and I divided it up into chunks of m, that's the maximum possible number. Max possible number. Okay? But then I've actually taken all the mass and divided it into boxes, the objects of mass m. Okay, that's what this means. The full density divided by m, that's the maximum number. So not all of these are structures, and the ones that are the fraction of structures at that mass. And I get that by taking the derivative. Or if you want, you can take some deltas instead. Times df. So that's the number of structures greater than mass m. But I don't want all of them. I just want the ones in a small range of dm. dm. Okay? So that's fraction of objects at that mass. Okay. So that's what you need to count galaxies, right? This is the maximum number, and here I just want to calculate the fraction that actually formed objects at that mass. And then I can put that in. It's not too hard to do that, except you need to get this factor of 2, and then you need this expression here. The derivative here is going to be just the exponential argument. So your df dm 2 times this is going to be 2, the square root of 2 pi, and then a bunch of sigmas, etc. So sigma of r, e to the minus delta, 2 sigma squared. And let me see, where's the other ones, is the dm. So then it's the derivative of that. So it's the sigma r, it's a half times 2. And I think that's all the ingredients you need. Oh, it's the d sigma d, that's this one, d ln. Sigma of d ln m. And then you multiply that by the rho over m, and you get this expression here, which is the Press-Schechter mass function. Okay. Oh, sorry, there's a 1 over m missing here. So 1 over m here. Just from the So that function is now based only on our understanding of the dark matter density structure, its Gaussian behavior. We know how to calculate this sigma, because I went over that earlier. If the power spectrum is a power law, you can put that in here, and you can get an estimate for sigma of m. Or if you have the power spectrum in a more complicated form, you plug it into a computer code, and you can calculate sigma of m. And that then calculates the number of galaxies at a given mass. And you can see it has some dependency on the mass that's exponential, like the mass function is. When you actually put that in, the dependency here on the mass, if you remember the sigma of m, the sigma square of m, is proportional to m to the minus m plus 3 over 3, if I can remember correctly, which I probably don't. 6, 3 or 6, never remember. Now if you put that in with some power n into the exponential, you see it's not going to depend like e to the minus m. It's going to depend on e to the minus m to some power. And the consequence is that it doesn't turn off quite as fast as the galaxy mass function does. Likewise, on the faint end where this becomes irrelevant, it's mostly going to be dominated by this term, which is m to the minus 2. And the observations have a slope of minus 1.3, 1.4. But you're getting quite close. Okay. So what we are saying, when we then run simulations, and I think that's probably my next slide, when you run simulations, you can then compare these predictions to simulations and see whether they get the right answer. And that's what this figure here is showing. The dotted line in all these panels is the Press-Schechter mass function, the one we just derived. The data points here are points from simulations. And you can see that it doesn't do a really good job, right? But it gets the overall shape quite similar to the simulation, but it underpredicts a bit here, it overpredicts a bit here. These are different cosmologies. This is the cosmology we think we live in. And, you know, it's not bad. It does a pretty good job for being a, 2-3 lines of derivation. But it's not quite satisfying. So the black line here is a much better fit and has this slight modification to the Press-Schechter function. So this is the Press-Schechter function. Here is a modification of that based on work by Schett and Torman. And the main difference here between this work and what I was doing now is that they did not consider spherical regions. And the reality is that dark matter halos are not spherical, they are ellipsoidal. And if you take into account that you have ellipsoidal collapse, so that one axis is going to collapse more quickly than another, then you get a slight modification here. And they put that in, and you can see that now the black line is really very good agreement with the data in here. For really high precision work, what people do is they actually don't do this, they use the simulations directly. But until only a few years ago, this analytic approximation was what people did in everywhere. And it's still, this sort of slight modifications of it are still what most people will use in calculations. And it's all based on exactly the argument I just gave, which from a physical point of view actually is almost nonsensical. So that's one thing. The next thing is that's the number of halos. So now you know how to calculate the number of halos. The next thing is to understand what the shape is of these halos. Okay. I'm not going to talk about the ellipsoidal shape. I'm just going to talk about what's the trend as a function of radius. And often when you're in the mood of doing things simplistically, you just say, oh, well, these halos are isothermal. If they're isothermal, if they have constant temperature, then their density distribution goes as r to the minus 2. In that case, the density distribution looks like this. It includes the temperature, which is constant, and the r to the minus 2. And this is the estimate of the mass. So can anybody see why this is not a very useful term in general for describing dark matter halos? If you look at the mass relation in particular, it goes proportional to r. So the mass of this halo would never converge. The larger the r I take, the larger the mass. Eventually my halo would take the entire universe. So it's not a very useful function to use. So what we use then is we typically, if you absolutely want to use this, is you integrate this out to the virial radius. And then you stop it there. And it's called a truncated isothermal sphere. What real theorists use when they don't want to do hand-wavy arguments is they use a different profile. And it turns out that when you fit dark matter halos in simulations, they all have very, very similar profiles in functional form. There's a little bit of variation which functional form people like to use. This is the most famous. It's called the NFW profile. It stands for Navarro, Frank, White, of the 3 authors of the paper. And they say that this is essentially what the profile looks like. It goes as 1 over r in the very center, and it goes at very large distances, it goes as r to the minus 3. And that means that it will converge. There's a finite total mass in this structure. And it has a few parameters, such as its concentration, the relation between the virial radius of the halo, and the scale parameter, which tells how concentrated the mass is in the halo. This is then the density that people use. And they typically, you would then assume that dark matter forms these structures, and then baryons fall into these structures afterwards. And this press check the mass function that we just calculated, that's a very good estimate of the number of halos. It's not a perfect one, but it's a very good one. And what this is leading us to, is it leading us to a fundamental way of looking at the universe. We can look at the universe as being built up only by dark matter halos. Okay. Let's think that that's what's happening. Okay, the universe is dark matter halo, dark matter halo, dark matter halo. Baryons is just going to fill into that. But the dark matter halos are what's going to matter. And when people started developing this, it really started in the, say, around 2000. They came up with something called the halo model. And I'm going to go through this relatively quickly here, but I wanted to give you a flavor of what that actually tells us. I'm not going to do the full derivation. I'm going to try to emphasize the physics. And I'm going to start out by emphasizing the physics by going to the Netherlands. So as many of you probably know, Netherlands is a very flat country. It's very close to the sea. And if you went back 1,000 years, it was very often flooded. So what happened was that people would live on these small regions that were slightly higher than the surroundings. So these are settlement regions from medieval times. Okay? And they all settled in these, forget these red dots, which are modern towns, but they settled along these ridges that were slightly higher, so that when the floodwater came, they didn't get washed away. It was kind of sensible, because the people that didn't settle there, they did get washed away. And you see all these regions, linear structures. Now, this is a slightly different view of the same thing. Now you can imagine the settlements. In between these settlements, there wasn't really anybody living because it occasionally was flooded. There was not a good place to live, right? So the settlements of this country was basically built up of dark matter halos or high points in the environment. And that's where galaxies live too. They live in high points of the density field. They don't live in the low parts of the density field because the overdensity is too low. They have to live where the density is high. And these people, they lived where the physical height was high, so they could actually survive. Now think about now, you're in the medieval times, people did not move around a lot. So now let's think about this correlation function I introduced earlier. Let's try to calculate the correlation function of a person. Okay, so if you're inside one of these settlements, you have a high chance to find somebody else from your village, right? Because everybody lived there, very few people travel. You have a very low chance, if you live here, to meet somebody from here. So most of your correlation function on small scales is going to be dominated by structure within the village, where people live within the village. If you now think about the correlation function on large scales, if I'm here, well, then you don't care about what the distribution of settlements inside the villages are. You only care about where the villages are overall. So there are two different components to your correlation function. One is what's happening inside your village, and one is what happens between all the different villages on the large scale. So there is a small scale and a large scale correlation function that are fundamentally different. One has to do with villages, and the other one has to do with where it was safe to settle. Now let's look at galaxies. Or dark matter halos, rather. So this is the power spectrum, now in that annoying k cubed times p of k formalism as a function of k. So it looks a bit different from what you have seen earlier because of this extra k to the third power. This is the prediction of linear theory. And this is the prediction or the calculation you get if you run a full simulation and you calculate the power spectrum. And you see there's a lot more power on small scales in this nonlinear simulation than there is in the linear simulation. So what's the reason for that? And that's where this halo model comes in. So the halo model builds on two things. First, it builds on that the density distribution of halos are universal. So you can always write the density of a halo as the mass of the halo times a profile function that's constant, that might depend on a few parameters, but the overall functional form is the same. And the second one is that we can decompose our correlation function into stuff inside the halo and between halos, inside the settlements, between settlements. And then we got these two terms, the one halo term inside the halo and the two halo term between halos. And that's the decomposition. And since this is on very large scales, that is very close to a linear prediction. Because here, on very large scales, the universe is in the linear regime. And indeed, you can do this. You can calculate these things. And you can actually find that the universe, the full power spectrum, is composed of this 2 halo term, the large scale, and all these different terms for the inside of the halos. Let me just jump past this. There are many different versions of this. These are observational data. And also in observational data, this is kind of a correlation function, but on the sky. Again, you can see there are 2 scales here. On large scales, the linear predictions, the dotted line here, works really well. On small scales, it doesn't work well at all, but the predictions for this 1 halo term, which adds up to give you this black line, I think. Yeah, the black line gives a very good fit to the data. It basically says that the universe can be decomposed into these 2 terms. And in that halo model, what's also useful about it is that it separates 2 different entities. It separates what's called a central galaxy. A central galaxy is sort of the galaxy that the dark matter halo belongs to. See, our picture of galaxy formation is that galaxies form inside their dark matter halo, but then these things collide. So now I've got this galaxy that's crashed with another dark matter halo. How do you relate that? Well, usually there is a bigger galaxy, a bigger halo, and the galaxy that belongs to the bigger halo will typically stay in the center of the halo, and that becomes a central galaxy. And then there's a bunch of satellites that orbits around inside the dark matter halo. And that separation is very useful because these galaxies orbit around here and they are affected by different physical processes than the central ones. And so we do that, we then combine that into this halo model. I mean, you can do the long list of power spectrum and you get a list of power spectrum of central, satellite, and satellite. I'm not going to go through all the details of it because I ran a little bit over time with this particular thing. And I don't want to spend too much of my time on it. But you can actually use that to then try to understand what's the distribution of galaxies of a given luminosity given the mass of the halo. And that's what people have done in the previous situation. Those are called conditional luminosity functions. I think I had the definition of it here. So the conditional luminosity function is the luminosity function, the distribution of galaxies with a given luminosity given the mass of the halo. And they are kind of the components that you can then multiply by the mass function to get the true luminosity function. And when people do that, this is the kind of distributions they get. And there's an interesting aspect to them. So it's probably easiest to start on the bottom right. So this is the most massive halo. And what they're finding when they look at the most massive halo, you remember previously when I was showing you the mass function, it's a nice, smoothly rising function. Here, this is close to a mass function. It isn't at all, right? It goes up and then over like that. And the reason why it's going up and over like that is that this bit here are the central galaxies. And these massive halos have some very big, very bright central galaxies, and these are the satellite galaxies. You go down in halo mass, you go up in halo mass, you'll see that you get more and more of these satellites because more and more galaxies have fallen into these halos. So the relative number of satellites become higher and higher. Here, in these ones, the small ones, these halos are so small, there basically hasn't been any other halos colliding with them. Very few at least. And that's why they haven't got many of these satellites. But in these ones, there's a lot of halos that have collided with them, and you get this whole distribution. And you get to the most massive halos where most of the galaxies are going to be satellites. And it's a combination of all these functions that really give you this nice, smooth distribution. So these mass functions that I'm giving you is an average mass function of the universe. It might not be the right mass function for a particular galaxy cluster or galaxy group, for instance. I had forgotten I put that sign single in. Okay. So I think now a good time to round off. And these are probably the bits I really would like you to recall from today. One is that the correlation function, which we talked about in the beginning, and the power spectrum are related by a Fourier transform. That's quite important. The other thing we looked at, which it seems like you understand, I think you understand, is that the power spectrum evolves and you get a characteristic scale set down by the epoch of matter radiation equality. So that gives a characteristic scale in the power spectrum of galaxies, in the distribution of galaxies in the sky. The spherical collapse model is another thing which is important. It's a spherical collapse. You can solve its nonlinear evolution. You can link that nonlinear evolution to the linear evolution, and you can understand when objects form. Using that, you can then calculate the number density of galaxies or dark matter halos as a function of mass. And if you remember the halo model, then that would be good, but I didn't spend enough time on it that I really will trust that you will. But these ingredients here are all you really need in order to make fairly decent estimates of what the galaxy population will look like. Okay, so that I think is a good time to end. I don't have any further slides here. Tomorrow, I think I'm going to move more to radiation and baryons and not so much on dark matter. Hopefully most of dark matter is done by now, and we can move to some of the more shining aspects of the universe. So if you have some questions about this aspect, the dark part of the universe, then now or tomorrow at 9 o'clock in my office, or tomorrow next lecture is a good time to ask me questions about that. Yeah. And for those that weren't here this morning, let me just remind you that that I created this problem set to be handed in, collection of the questions for handing in, and that's on the web page. And for tomorrow, oh, this is not this one. Sorry. Oops. Tomorrow I will go through one, essentially a simple problem or two of them rather. And I'm going to go through one problem which by experience I see people find a little bit confusing when they look at it the first time. Have a look at it, see if you can solve it by tomorrow. We will go through them tomorrow morning. It's a useful thing to think about because it has to do with this entering the horizon and when things enter the horizon. Have your hand on, give a try. And then the second thing I'll go through is basically an application of the Press-Schechter theory that I just covered and how you actually use it. Because the way I did it now, I just derived it, and it might be a little bit confusing how you actually would practically use it. So I'll spend time tomorrow morning to go through these two problems. But it's very useful to have a look at them beforehand. You will get a lot more from it. This is a bit of work, so I don't expect you to. This you can do. If you start right on this one, you can do it in 5 minutes. If you start wrongly on it, you probably will take 5 hours. If you start on this one right, then it will probably still take you a couple of hours the first time around you try to do it. It's a bit fiddly, so but it's definitely worthwhile trying to see if you can do it. Okay, maybe you'll manage to do it in half an hour, and then I'll be impressed. Okay, I'll. Yeah. Yeah, it's fully possible.
Questions?
Anyone? Yeah. Also, I think it's quite hot today. Everybody's a bit. So.